I moved to then I moved to Hong Kong UST, Hong Kong University of Science and Technology, as a visiting assistant professor, and I was working for them for 2 years. But now I just kind of quit my job, and now maybe I'm giving kind of research break. Hopefully, I will be able to continue with my publications.
My apologies to
no problem.
The last contact, sorry.
Yeah, they didn't remove me from their webpage. So when you just Google me, this is the first thing that you find. Sorry about that. Okay, so today I will be talking about machine learning application to finance. I think this is one of these hot topics. And when you ask people, what do you think about fintech, financial technology? There are different opinions, right? Some people just say that fintech is all about blockchain and also the Bitcoin, etc., right? And some people think that it's this application of machine learning to financial data, right? I think I'm from the second, I'm following the second view. And in my teaching at especially Hong Kong UST, since I just taught mainly courses for UG and then masters and also for the PhD students, and I was always focusing on the implementation of machine learning to financial data. And it could be structured or unstructured data, text data. But anyway, I just want to explain what is machine learning applications to finance. And in this work with my co-authors, Tao Huang and Michael Ching, we basically focus on structured data, not text data, okay? And we are trying to solve a problem which is simply empirical asset pricing, okay? What is empirical asset pricing? Probably most of you do not have background on empirical asset pricing. Let me explain what is empirical asset pricing. Empirical asset pricing tries to understand why some assets are given higher returns, expected returns. Let me give an example, such as when you look at the return of Apple, right, over the last 10 years, it has a huge return, right? Why is it the case that we observe these returns, right? And obviously in finance, we have some models to model the expected returns, okay? And the first model is just like from this quote, he's saying, John Cochrane is saying that we also thought that the cross-section of expected returns came from CAPM. The third model is CAPM, okay? In 1960s, people just tried to explain those excess expected returns using a single factor. What is the single factor? Excess return on the market portfolio. What is a market portfolio? It's simply an index like S&P 500. But then we have a zoo of new factors, just like what John Cochrane says. Here the zoo refers to different factors, different characteristics, is very similar to animals, right? Each animal has a different characteristic, right? So this is why they coined this term zoo of new factors. And indeed, I will just try to explain the increasing number of factors, okay? So in 1993, such as we had 40 anomalies that beta cannot explain. So what is the meaning of that? The meaning is this. Indeed, maybe I should just try to explain what is an anomaly. An anomaly is, let me say, I'm using CAPM to explain those observed expected returns, right? But if I cannot explain, if I just run a regression, right? On the left-hand side, the returns that I get using that factor, right? That new characteristic. And on the right-hand side, there is only one variable, which is simply excess return on the market portfolio. And if I just run this regression, and if I observe some alpha, which is significant, alpha means the part that cannot be explained with the model, right? If it is significant, then we can call this anomaly, okay? And as you see here in 1993, we had 40 anomalies. And what about in 2003? It doubled to 84, right? And in between 2004 and 2012, we added 164 new anomalies. And obviously, you can observe the tremendous increase. And this is, by the way, from Harvey et al. And also this RFS refers to the name of the journal, Review of Financial Studies. It's the maybe second or third top finance journal. And what about Harvey and Liu 2019? There is a working paper which is simply trying to document all these new factors, and they are simply finding that there are almost 400 factors, right? This is why they call this factor zoo. By the way, if you have any question, please just stop me and ask. And let me just start with our motivation. Our motivation is first, there's an increase. I just explained, I tried to explain the increase in those, the size of the factors. So we need to simply tame, we need to downsize this, right? We need to somehow make them, some of them not an anomaly, right? We need to come up with a model. This is what they're trying to do in it. And what is the reason for this increase that we observed? First, it's oversimplification, right? We use linear models. And what is the reason for linear models? Since CAPM is a linear model, right? Indeed, CAPM has a theoretical foundation. And when you just do all these derivations, you observe that it's a linear regression simply, right? And a single factor. And also finance people like, obviously, linear regression, linear models. Why? It's easy to explain, right? And there's another reason why we keep observing new anomalies, since in the end, we only use a limited number of factors, okay? Let me just try to explain how do they come up with these factors. First, let me say, I just read all these finance implicit pricing papers, and I couldn't find a factor or a firm characteristic, which is, let's say, idiosyncratic volatility, which is there, but let me assume this is not the case. Then if I just create my portfolios based on that factor, based on that firm characteristic, and if I cannot explain those observed returns using stylized models like from a French 5-factor model, then obviously I will just simply say that this is an anomaly, right? And this could be an anomaly, okay? This could be a factor, okay? This is basically what they do. And obviously here the question is why they simply use from a French 5-factor model, but all other factors, right? Since in the end we are saying that we have 300 or 400 new characteristics, new anomalies. Why don't we use them? Since in the end this is not what they do, okay? So this is one of the reasons that we keep observing new factors almost every day. And what are the potential solutions to this increase in these factors? First, if you look at such as Harvey et al. 2015 paper, what they do is they simply increase the threshold for p-statistics. And the reason is very obvious. Since in the end, let me assume that we have a data from 1998 to 2016. And what I'm doing is I'm just trying to understand whether if I just try to create a portfolio using idiosyncratic volatility, whether from a French 5-factor model will be able to explain, right? And if I'm using the threshold of, let me say, 2 for the p-statistic, maybe I will be able to see that it's really the case that the alphas are significant, right? But the question is, am I using the same data for all these different factors? Yes, right? So which means it's basically efficient, right? Isn't it? So I just keep trying on the same data, I just keep trying different factors. Eventually, I will find something, right? And so what is their suggestion, Harvey et al. 2015 RFS paper suggestion? Instead of using the threshold of 2, what if we just use 3? Then most of these anomalies will disappear, okay? And what about the second approach, second class, downsizing? Such as there's a paper by Freiberger et al. 2020, again RFS paper. And what they do is they use lasso. What is lasso? Lasso is basically, again, linear regression. But this time they try to decrease the number of factors. How? By adding a penalization term to this linear regression. Okay? They just basically try to make those coefficients 0. Okay? This is basically lasso. And the second paper is also Feng et al. 2020 Journal of Finance paper, and which is basically marrying or combining the lasso with Fama vectors. Okay? And this is very important paper indeed. Why is that the case? Since in the end, they're just trying to explain that you can use this approach to check whether a new anomaly is really an anomaly. Okay, so I think this is why it's a very good paper. What about other approach like aggregation? And Stenbaugh and Yuan has a real good paper. What they do is they try to combine different anomalies into some groups. Okay, they have 11 of them, and they just simply create two groups, and they, instead of creating their portfolios using a single factor, they simply take the average of these rankings, okay? And we can call this aggregation. And there are two other papers which are doing pretty much similar things. But I want to focus on the last paper, Gu et al. 2020. And here the important names are Brian Kelly and also Dachang Xu. Brian Kelly is a very, I think, well-known professor on machine learning in finance. He has lots of papers. I strongly advise you to read his papers. And he's from Yale, and he's the, I think, the head of the machine learning at AQR Capital. And Dachang Xu is working for Chicago. I think he's in statistics department. And this paper is very similar or very close to what we do here. So what they do is they're just simply trying to use all the machine learning models, okay? Like, what do they have? They have linear regression, they have generalized linear models with penalization, dimension reduction, they have regression trees, and also neural network. And they use all these different models, and they simply check the performance, the forecast, okay? So what we do is at each month, using the previous data, we just try to come up with the best prediction for next month's return, okay? This is basically implicit pricing, right? But in the end, we are trying to explain expected returns. But right now, we are just starting with the forecast of next month's return. And what do they do? What do they do? What do they find, I should say? First, they just find out that neural networks and regression trees are the best performing methods based on the forecast. And their aim is not indeed to explain why machine learning models are working much better than classical models. It's not their aim. But they try to say something about that. They simply look at the feature importance. Since in the end, when you train your machine learning model, you have two, obviously you have a training data, and then you need to test the performance on the test data, right? On the trained data, when you're training your machine learning models, you can check the feature importance, okay? So even some of these Python libraries allow you to do that. And you can simply observe which features are really important, okay? And simply what they do is they just keep doing the same thing. They just keep observing what factors are really important for each of these machine learning models. And they observe that some of these characteristics keep appearing at the top. And what are those things? Like price trends, like momentum, right? 6 months momentum. And liquidity, like let's say turnover. Okay, and what about volatility? It's simply idiosyncratic volatility we can add here. Also, the valuation ratios. So as you see, there are some factors which keep appearing on all these machine learning models. So they say that we cannot explain why machine learning is working really much better than classical models, but at least we found out some factors, right? We found out some factors are doing much better. I mean, at least they keep appearing in all these models. So they should have something to do with the machine learning performance. This is what they say. And what about a summary of our work? Let me just check the time. Okay, so what about a summary of our work? First, instead of using all these machine learning models, just like Gu et al. 2020, we simply use 3 of these models. The first one is a linear regression. And the second one is extra trees, and the third one is gradient boosting trees. Why do we use them? Since indeed these models are used in the industry a lot. Okay, we are just trying to align ourselves with the industry and industry practices, and we simply create long-short portfolios, just like what the literature does. And how do we do that? We just use machine learning models. We ensemble them. We combine their predictions. I will explain how we do that. And then based on these forecasts, we create long-short portfolios. What is the meaning of long-short portfolio? It means based on machine learning predictions, right? Let me say we have 1,000 stocks, and machine learning is giving us the returns for the next months, right? And then if we simply sort these returns, and if we just get the top 10 percentile, if we buy those stocks, right? This is long side. And then if we tell simply the short bottom part, right, and we call this shorting, and we will simply look at the long minus short performance, okay? And we are simply creating long short portfolios. And then we check the performance, whether we can explain the returns, realized returns, using these prominent factor models. And there are, indeed, at least we used 4 of them: Fama-French 3-factor, Carhart 4-factor, which is simply addition of momentum to Fama-French 3-factor model factors. And then we have Fama-French 5-factor, which is simply addition of 2 other factors to FF3, which are profitability and also investment. And also we have Q4, which is Ho et al. 2015 paper. FF5 and Q4 are pretty much almost the same, since they are using almost the same variable, but this one is removing one of these factors from FF5. And we also try to say something on the test data, right? Since in the end, we are not trying to simply follow the footsteps of the previous papers, since the previous papers are focusing too much on the training data. This is why the results are in sample. Instead, we want to look at the test data, right? We want to see the performance of, obviously, the machine learning, and we are just trying to understand what machine learning is buying and selling, okay? And we call this a reverse engineering technique. And how we do this thing, let me explain a little. So, so what we do is, on the long side, machine learning is saying that you need to buy those stocks, right? And on the short side, machine learning is saying that you need to sell these stocks, right? And imagine that we are focusing on a single characteristics like idiosyncratic volatility. So I can simply look at the idiosyncratic volatility value for each of these stocks on the long side. Can I do that? Yes, right? I'm just talking about a single month of the test period, like 1998, January. And then I can just simply take the average of these values and it will give a single value, right? And if I just do the same thing for the short side, let's say I have 1,000 stocks there, and I can just check the idiosyncratic values for each of these stocks. I can take the average of each of these values, and I can just check these two, I can compare these two values. And for each month of the test period, obviously I will have this difference, right? So as you see, I can simply compute the t statistic, and if everything is random, right, if that factor is not important, obviously that value should appear everywhere, independent of whether it's long or short. So this is why when I just take the average of the long and short side, I shouldn't observe anything. It shouldn't be important, it shouldn't be significant, right? But if it is significant, then it means machine learning is aligning itself with that factor. Somehow it's understanding that factor will be important. Okay, this is basically what we do. So there are 3 contributions of our paper. First, we simply ensemble, combine different machine learning models. I think this is the first time, and this is the industry practice, by the way. And the second thing is we propose a new portfolio dissection reverse engineering approach, and we do out of sample analysis instead of in sample. And also we find out that our approach simply states that external financing, among most important ones, it could be an important factor. Since in the end, if you look at the Fama-French, let me say, papers, you won't observe any factor related to external financing. Okay, so it means maybe external financing should be, or something related to that, maybe a factors, right? Maybe in the future we will see some factors, some like Fama-French, let me say, instead of 5, 7 factors, and external financing could be there. This is what we are saying. And also, let me show the result. We are saying that indeed, not just some factors are there over the test period, but we also observe a change in their dominance, right? Some factors are really important, like idiosyncratic volatility around 1998. By the way, I will explain this, but 1998 to 2016 is the test period. We are just simply focusing on the test period, since it doesn't make any sense to look at the training period, right? Since we are training the machine learning on the training data. And then we are observing, as I said, we are just doing the reverse engineering to try to understand which factors are important. And when we just simply check the factor importance, we are observing that idiosyncratic volatility is important around, let me say, 2000, right? And what about cash flow is slightly less important, but still important. And it keeps becoming very important around 2008, around the financial crisis, such as. What about the external financing? External financing is very important around this time, especially after the Fed easing, right? After quantitative easing. And still it's important, right? What about min and max? Min and max, they are very close, right? So when max is important, min is also important. We can state that, I think. And min and max, by the way, belongs to Rambali. And what min max is, let me explain a little, since I think it's one of the important papers. They're simply checking the minimum and maximum daily returns in a month, right? Okay. So as you see, we observe that some of these factors simply rotating, right? So some of them are important around, let me say, 2000, and then they're becoming again important around 2008, right? So I will try to explain this in future slides, but this is our main result. So let me explain how we did that, how we just created our machine learning portfolio. As I said, we used 3 different models. The first one is extra trees. Extra trees is basically a decision tree, but we train different decision trees, right? And then we simply instead of using the all, we use all the training data, but simply cutoff points are decided randomly, right? We are using obviously a machine learning Python package. And what about gradient boosting decision trees? Gradient boosting decision trees is obviously also a decision tree, but again, we just train decision trees, but we just simply train this decision tree based on the residual of the previous decision tree, right? And then we ensemble the results. And this, we use a package which belongs to Microsoft, by the way. I think it's working quite well. And also we use another machine learning model, which is simply linear regression. But here we use kind of 2 variable combinations out of theta 1998. What is theta 1998? Let me explain. We have 106 characteristics in total. What are those characteristics? Like idiosyncratic volatility, price-to-earnings ratio, etc. All of these, right? And we try to downsize this list, and we call this theta 1998. Why is that the case? Since in the end, as I said, we will be creating some linear models, right? Using only 2 variables out of this data. Okay, why is that the case? Why do we use 2 or 3 variables instead of using all of them? Since I didn't explain this, but all these decision trees is using all the variables, indeed, all the characteristics, 106 of them. But what about linear regression? Why do we use just 2 of them? Since in the end, we know that linear regression works very well, right? If you just keep increasing the number of variables, it works perfectly, right? On the training data, but on the test data, it will not perform well, right? So they say it will not generalize, isn't it? So that's why we need to use either 2 variable case or 3 variable case, and we simply stick with 2 variable, okay? And we simply combine these machine learning models. How do we do that? So here in this figure, we explain, we have a factor zoo, we have 106 characteristics in total, right? And we train these different different machine learning models. And here we just have 3 classes, but not necessarily we have 3 models, right? Since in the end we have different extra trees. We have, if you just keep changing the parameters, such as, right? Such as we generally train 3 different gradient boosting decision trees, okay? And also linear regression obviously depends on how many number of combinations of linear regressions we have, right? Let me say if we have 7 features in theta, then obviously we will choose 2 of them. So it means in total we will have 21 different models, right? And we just call this model 1 to model M, but we need to choose the model which is working best at a time in the training period, okay? If a model is never the best, right, then we don't include this in our list of models, okay? And what about theta? I think I need to also slightly explain this, how we come up with this theta. There are different ways to downsize the list, right? The easiest way is you can simply use correlation. You can simply look at the correlation of these factors with the next month's return, right? This is the easiest way. And nobody is saying that you shouldn't do it. You shouldn't use this approach. But what about implicit pricing literature? Since in the end, when you look at these models, there should be something we can do, right? And how did we do that? We simply run regressions. We just simply created some portfolios based on single features, right? So, like idiosyncratic volatility. And then we just simply check the return of long minus short portfolios return. And we just try to explain this with form of range 5 factors, right? And we did this, let's say, for one of these factors. And we will get an alpha, right? Alpha is the part, if you recall, I just talked about that. Alpha is the part that cannot be explained by the model, right? And if we just keep doing the same thing for all these characteristics, in total, we have 106 of them. And we can simply look at which ones are really important, right? Which ones are significant and which ones are not significant. And among the significant ones, we can simply rank them, right? We can just take the absolute value and we can simply sort them. Then we can just get, let me say, top 7. In our paper, we have a result showing that 78 of them is good enough. Okay, so you shouldn't use more since their out of sample performance will deteriorate. Okay, and then what else we do? We just simply stack these models. And how do we do that? We simply use a decision tree. Okay, we simply train a decision tree which is using theta values. Let me explain how we do it or why we do it. Why do we do it? Since in the end, at a month, like I'm on January 2000, right? And I want to understand which of these models perform best, right? Can I simply condition this on the theta? Yes, I can, right? I can simply look at the theta values like idiosyncratic volatility or whatever these features are in theta, right? And I can simply try to understand in which case, right? In which case, one of these models is the best, right? So that I can simply train a decision tree, which is linking the theta 98, so which means those features, to the next month's performance, right? And what is the advantage of that? So that at each month, I will be able to simply assign probabilities to these models. Okay, this is what we did. And then we simply pass to, let's say, the test data, and we make predictions on each of these months, right, for each of these stocks. And we create long, short portfolios. It means buying and selling, right? Simply buying the 10 percentile, right? And selling the 10 percentile. We call this long, short portfolio, if you recall. And then we simply check the performance. Okay, this is simply the model. And here we have an algorithm. I think I explained this thing, but let me just be fast here. Stage 1 is split the data into 2. We have from 1980 to 1998 data as a train, and 1998 to 2016 as a test. And on stage 2, what we do is we train the machine learning models. As I said, we have 106 characteristics in total. And we train extra trees and GBDT on all these characteristics. This is the advantage of decision trees. These are non-parametric models, right? And since this is non-parametric, it will work well if you use all these characteristics, right? Even some of these characteristics have non-value, not a number, it will still work. Okay, this is the advantage of these models. What about neural networks and linear regression? It will not work, right? So which means we need to handle those things. What about FF5 and Q4? We are simply using these two stylized models to rank those features and to create theta 98. So if you recall, I explained this. This is simply a downsized list, right, of these features. And we use two different approaches. Why? We want to check if you use this approach or this approach, whether it's changing anything, right? So kind of robustness and analysis, right? Whether our results are simply depending on the selection of, let me say, theta 98, right? And what else? We simply use theta 98, this list, to create two variable linear regression models. And then we compare to R value, which is a kind of metric to understand which model is doing well on the trained data. It could be used obviously for also test data. And then we simply remove all these models which are not best at one of these indeed training data. Okay. Then we simply decide which model is the best, and we train a decision tree as I explained before, and this decision tree is on the theta, right? Since, as I said, we have the theta value, we have the loss factor values, and we simply find out which one is the best next month, right? So that we just train the decision tree, and this is called stacking. And based on obviously this stacking, right now we can make predictions, right, for each of these stocks on test periods, right? And then we can simply create the machine learning portfolio, which is buying the predictive winners and selling predictive losers, okay? What about our data? Our data spans from July 1980 to December 2016, and this is from compass.crSP. This is Wharton's data, right? And you need to subscribe to this data set so that you can use it. And these are all standard things on finance papers. I don't need to explain this. And in total, we have 106 characteristics. Indeed, this is very similar to indeed Brian Kelly's paper. They have also, I think, around 106, maybe 105 characteristics in total. Okay. And what are our findings? The first one is, the first result is we found significant alpha average. Since in the end, we have, what we do is we look at whether we can explain this alpha, right? If you recall, alpha was the part that cannot be explained with a machine learning, with a classical factor model, like from a French 3-factor, current 4-factor, or from a French 5-factor, or Q4. And indeed, we just found out that alpha ML is significant for each case. So we cannot simply say that the performance is coming from one of these factors, right? And all 16 alpha ML are significantly positive. And out of 32, 29, indeed, predictive winner and predictive loser alphas are also significant. So not just long minus short, but also predictive winner and predictive loser mostly significant indeed. And also magnitude and t-stats of alpha both monotonically increasing from predictive loser to predictive winner. So let me explain this thing. So here, as you see, we have in the bottom percentile, right? Indeed, this is predictive loser. So this is the return that we get. This is the average return that we get. And as you see, when we move to predictive winner, right? So the expected return is increasing. Okay, there is a monotonic increase here that we observe. And what about the alpha? This is 2.11 indeed percent. This is monthly return, okay, for all the test periods. And this is significant. The number that we write inside the parentheses is basically t statistic. And we just try to explain this performance using FF3 and then FF5, and we fail, right? Since when we just try to explain, we need to look at the alpha. As you see, the alpha is 2.48 and 1.86. They are still significant, okay? And the performance, what about the performance? So obviously, we need to look at the performance of the machine learning where on the test data, starting the first month of the test period, right? If you just keep using the machine learning models, and by the way, I need to also explain this. If you look at some papers, they have different approach, right? To choose or to split the data into train and test. And in industry, what they do is, such as at each month, they use all the previous data, and it makes sense, right? But in our paper, we are very close to indeed computer science papers, machine learning papers. What they do is they just divide the data into 2 equal parts, train and test, and they never touch the test data, right, to train the models, and they observe whether it will do a good work, right? This is simply showing that if it works, it's showing that indeed machine learning is learning something, right? Indeed, we just use the previous part of the data, right, train data, and then we never trained those models on the test data. From 1998 to 2016-11, we did nothing, right? And if you do this thing, the cumulative return, if you just have $1, right, at the end of the test period, it's becoming around $90. Okay, so the performance. What about these different lines, I just mentioned that, you can use different approaches to come up with data, right? And so the best one is FF5, and the best one is Q4, right? And also maybe the correlation is somewhere here, okay? So as I said before, there are different approaches, and we just use them and just try to see the performance, okay? And what about main finding 2? The machine learning portfolio's monthly dominant characteristics is insufficient to beat the machine learning portfolio. Now, we just try to explain this performance. Since in the end, if you just send your paper to a finance journal, obviously the first question is not whether your Sharpe ratio or expected returns or the realized returns is good, right? But how do you explain this, right? What is the source of alpha, right? This is the first question that you get, obviously. And for that, what if we just try to explain this using the characteristics? So one idea is maybe machine learning is really, really good at picking the right characteristics among the factors zoo, and they are simply leaning on them, right? They are just increasing their, let's say, weight, right? This is one explanation. And so we are saying that this is indeed insufficient. How did we do that? We simply create a shortlist K1 characteristics from the zoo. And how we do this, we just, as I said before, we just simply use reverse engineering. Okay, I think I explained the procedure, right? We are simply looking at the values, such as for idiosyncratic volatility. We are looking at the idiosyncratic value for each of these stocks on the predictive winner and predictive loser side. And then we're just simply taking the means and just subtracting. And we have this for each month of the test period, right? And we can look at we can compute the t-value, right? And if we do this thing, obviously, we will have the important characteristics, okay? And now we are saying that if we simply use these characteristics, it will not be important. And how do we do that? We simply use stem bound again. So just like what they did, what if we just use all these characteristics inside this K1, the important characteristics, right, shortest characteristics, and we just create a single portfolio, right? And we call this RK1T, that this is the return. And we are just trying to use this return to explain the machine learning's performance. And indeed, when we run these regressions, we observe that indeed the alpha, right, the part that cannot be explained, is still positive, but indeed dropped. Okay, so which means some of the performance is indeed coming from those factors. Okay, but this is not all. Why? Since in the end we are not seeing alpha is 0 or it's not significant, right? We are not seeing that. It means still machine learning is somehow picking maybe the correct characteristics, but also doing some rotation, right? Maybe it's increasing its importance, etc. Okay. And what about the finding 3, the month dominant characteristic K1 in the machine learning portfolio? And what we do is we simply check the top 3 characteristics, right? And indeed only 10 characteristics suffice to fill 99.1% of rank 1. Okay. So we just, I think I just showed the graph, right, previously. Okay, just show it later. So when we look at the heat map, right, you will observe that some of these characteristics keep appearing, right? So they have rank 1 at 1 month of test period, and then maybe 3 months later, they're again rank 1, okay? And here we are saying that indeed we have only 10 characteristics, and which will simply fill up the rank 1 to rank 3 spaces, okay? And they are simply moving in and out of top 3, but they largely remain in top 10, okay? And what are those characteristics? What are those top 10 characteristics? The first one is idiosyncratic volatility. These are all anomalies, right? But we are saying that currently they are important, okay? Like idiosyncratic volatility, cash flow, GXFIN, what is that? This is growth in external financing. And indeed, these characteristics were never important. Maybe you cannot find that many papers which is giving importance to these factors, but maybe we are saying that in the future they will be important, okay? And we just give these results. What else? What about, and we are simply saying that they cannot be factor model blind spots, since in the end, this is not simply pre-publication anomalies. Indeed, there's a paper at least which is simply looking at whether the factors are losing their importance. This is not like something like that. Why? Since again, I will show the heat map. Some of these factors are dominant at one time, and then they're becoming dominant maybe, let's say, 1 year later. Okay, so it's not like that. This is what we write here. And none of them are factors. Obviously, none of them is appearing in one of these stylized models, like from a French 5-factor model. And 2015 factor models are sufficiently up to date to explain that 2016 factors do. Indeed, from a French 5-factor model is up to date, since in the end they came up with this model in 2015. And most of these factors that we use is before 2015. Okay. So this is why we are not saying that, you know, when they just write this paper, they couldn't see these, they couldn't observe these factors. It's not the case. It was known. Okay. And what is our conjecture? The alpha ML, the alpha, is coming from time rotation among dominant features. Okay. So we have these features. Indeed, previously we have done that, right? Even if we have those features, we couldn't replicate the performance of machine learning portfolio. Right? And for this, we have this heat maps. And if you look at the heat maps, you will observe that there are 3 trading characteristics important: 4 internal financing and 3 external financing. Okay. And we also observe a cone movement in ranking of idiosyncratic volatility, mean, and max. This is, by the way, constraint, arbitrage constraint related factors, right? These trading factors. And what about cash flow? By the way, this is simply operating income before tax and depreciation, and this is external financing. And we will also observe that they are moving together. Okay, so they are becoming important at around the same time, and they are becoming less important around the same time. Okay, so. And how do we explain this? How do we link this indeed to the macro variables? We are saying that this is related with credit cycle. Let me just try to explain this. Indeed, let me say, when you are looking around, let me say 2011, right, which is Fed's easing, right, quantitative easing. So as a result, the cash is abundant, right? So as a result, the idiosyncratic volatility, right? Idiosyncratic volatility. So I should just look at this thing, min and max. At least min and max, they are not important. Okay, why is that the case? Since these are related with indeed constraint arbitrage, right? What about external financing? This is becoming very important. Why is that the case? Since in the end, when cash is abundant, nobody cares about whether that stock idiosyncratic volatility is high or min and max is the problem, right? They only care whether they can fund their operations, isn't it? So this is why growth in external financing will be indeed important. Okay, so this is how we try to explain, but this result is a little preliminary, so this is why I don't want to talk about that too much. And the last part of the presentation is looking at this time variation and how we do that. What if we just create another list of factors? Okay, but this time what I will do is what I will do is, instead of focusing on the machine learning portfolio, which was, if you recall, K1, right, the important factors in the machine learning portfolio. Instead of this thing, what I will do is I will simply create a list of factors, right, which are really important, right? Can I do this thing? Yes. So I can simply look at the returns, right? And I can simply look at these factor values, right? And I can simply create a list of factors which are really important in the next month, okay? And we call this K2. And we just plot in the we graph 2 plots, and we compare them. What is that? The red, the black one is machine learning return. What about the red one? It is indeed simply the representation or the proportion of K1 characteristics that appear in K2. Okay, what is that? it is simply showing what portion of K1 characteristics appear in K2, right? So which means, is it the case that machine learning did a really good job, right? If it is 100%, so what is the meaning of that? Indeed, all these machine learning important characteristics, right? Machine learning is leaning against those characteristics, right? And they will be really important in the next month. Okay, if that is the case, what should we observe? We should be observing a high machine learning performance, right? Isn't it? And this is what we are trying to understand. And if you look at the graph, we will see that indeed there is a co-movement in a number of peaks and troughs in the machine learning portfolio return. So it means when the proportion, the representation ratio is increasing, we should be observing an increase in machine learning return, right? Machine learning portfolios return. And when the ratio is decreasing, then we should be observing a decrease in machine learning return, right? So that we can simply understand that machine learning is doing a really good job at finding the correct characteristics at the right time. Okay, this is basically about time variation. So let me conclude my talk. First, we simply combined or ensembled different machine learning models, which is a standard approach in industry. And we simply saw that indeed the machine learning performance cannot be explained with the classical models, like from a French 3 factors to from a French 5-factor models. And also the machine learning portfolio identified 10 prominent characteristics, which are given in here, from idiosyncratic volatility to mean, max, and also factors related with external financing. And they keep changing, right? We keep observing them. When we look at their rankings, it keeps changing, right? And this is why we say that it reveals a rotation pattern, right? And also, we can simply say that machine learning is good at predicting cross-sectional returns through time because it dynamically identifies prominent characteristics. And this is coming from where? This is coming from this graph, okay? We have this result. Okay, so do you have any questions? Was I too fast, by the way?
Thank you. Thank you very much, Halis Hocam. That was really a very nice study on the application or the design of the machine learning in the finance problem. I enjoyed very much. I will ask to the participants if they have any questions. We are going to allow them to just ask questions also by showing using their video as well. Yes, please let me know if there is anyone who would like to ask question to our speaker. I don't see any hands up. If you allow me, I have a question. I mean, I am very much, Devin Hoca is willing to have a question. Please go ahead.
So I cannot hear.
All right. Halis Hocam, thank you very much for your presentation. Very interesting. And I think it's to my knowledge, it's the first talk that we had at the Institute on these machine learning algorithms applied to investment. My question is the following. Now you train your data, you train your algorithm on data starting from 1980 to 1998, right?
Yeah, exactly.
So, and then you apply your algorithm starting from 1998 to 2016.
Yeah, exactly.
So my question is a more philosophical question, perhaps. Now, wasn't there like didn't the world change a great deal from 1980 to between those two periods. I mean, for example, in the 1980s, there was no internet. And we didn't have this very low interest rate environment and so on. There are tons of change. So there was, for example, the Soviet Union. There were all these big differences between those two time periods. So it's surprising to me how, like, an algorithm that's trained on this very old data performs so well in an environment that's very different. So that was surprising to me, and I'd like to ask what you think about that.
Yeah, thank you for the question. Since indeed, this is when we start this paper in 2017, this was my argument. Indeed, my co-authors had different ideas, at least one of them. And if you look at such as Brian Kelly's paper, they pretty much use a different approach. Like they always change the trained data and they just use all the previous data, and they simply make a prediction on only next year's months. Okay, and if you do this thing, obviously you have the advantage, right? Just like what you say, you're training your model using up-to-date data, right? But the thing is, if you look at, so indeed we borrow machine learning from computer science, and personally I just want to look at what computer science guys are doing, right? And when I just check their papers, what they do is they simply divide the data into two, and they simply use the first part of data to train the models, right? And then feed the performance on the test data. And if machine learning is really working, it should perform well, right? If it is not, it shouldn't. And how do I explain the performance? Since in the end, it's correct that we train our models on the trained data, although maybe there are some differences, during these between these time periods. Still, we have this, decision tree, right? Since we simply train a decision tree, which is simply looking at the theta values, those factors, right? At least some of them, 7 of them, and trying to understand at which time, right? Such as when idiosyncratic volatility is that value, when momentum, let me say, is this value, which model will perform well, right? So indeed, that part, the probabilities keep changing. I should state that, right? Isn't it? But this is not creating a look-ahead bias. We are not using any data to train, since we also train that decision tree using only the training data, right? But that part can explain, since that part is knowing, right, at which time period, right? When, let's give an example. If we had only one variable, let me say idiosyncratic volatility. When the volatility is up, right? When the economy is having problems and when the volatility is up, maybe one of these models is performing the best. Let me say linear regression, right? So in that case, the machine learning is simply assigning more weight, more probability to that model, right? Since that part is changing, okay? So I think I can explain. Indeed, the rotation part is coming from that. Otherwise, if we don't change the probabilities, machine learning wouldn't work well, right?
Thanks so much.
Thank you.
Any other questions from the audience, from the participants? I have a question regarding to the co-movement and the correlation. As these things are very much sensitive to each other, the stocks, also some macroeconomic indicators, how the machine learning algorithm or your design is coping with the autocorrelation, if there exists, or is it just eliminating it?
Yeah, exactly. Since in the end, it's also a very good question. Thank you. In the end, if you are using linear regression, right, we know that they shouldn't be correlated, isn't it? But indeed, if you're using a more complex model, a nonlinear model, right, like a decision tree, like especially a complex one, it can handle, isn't it? This is the advantage of bringing something from the machine learning literature. Indeed, decision trees. They can handle all these correlations. They can handle all sorts of change in the correlations, etc. Okay. So that's my understanding, and they are non-parametric. This is the advantage. And also another thing is, indeed, if we just do something like changing models each time, then obviously this will be, especially if you just look at the future, this will be cheating, and it will create a lookalike bias. And we are not doing that. The only thing that we do is we just include all the characteristics inside those complex models, right? And those models is designed perfectly that it can handle all these things. Indeed, especially the GBDT, this gradient boosting decision tree, as I said, that the machine learning library that we use belongs to Microsoft, and it works perfectly. Okay. Since in the end, if you use such as extra boosted trees, XGBI, I guess, maybe if you look at the machine learning literature, maybe 3 or 5 years ago, they were really hot. So they were using all of that model. But right now, if you just try to use that model using this data, you will observe that the performance is very, very bad. Okay. So what I'm trying to say is, if you use the state of the art, if you use all these very complex models and which are designed for basically this kind of job, it will do a perfect job. Okay.
You presented the cumulative graphs. So when you look at the just returns estimated and the other ones, does it follow, or is it free of the trend, or is it just coping with that also behavior?
Yeah, if you look at such as around 2008, we have a drop, right? Mm-hmm. But in the end, you cannot escape from that drop. Why? Since when you look at the stock, all of them are dropping, right? And when you create a long-short portfolio, you need to buy some of them, you need to sell some of them. In the end, you're bound to lose money, right?
Okay.
Now, it's difficult, what I'm trying to say. Around this time period, it's very difficult to make money out of by using this kind of machine learning model. I'm not claiming that you can understand, can do all sorts of work and it will work perfectly. It's not the case. But the important thing is obviously the long-term performance, right? In the long run.
Okay. All right. I guess there won't be any other questions, but I'm very, very much okay. We have another question from Oz Coach. I'm going to unmute him. Yes, Oz.
My question is that in these calculations, transaction costs are considered.
They never consider transaction costs. If you look at the finance papers, they never do that. Why? It's very difficult first. And, we don't have that data, also another thing, right?
Okay.
Why we never do that. So I cannot claim that, if you use this approach, right, you will make money. It's not the case. Let me also explain a little. Maybe we have a kind of problem, but all these papers have the same problem. One question is, when you start in 1998, there are some factors that we use, there are some characteristics that we use, which will be discovered later. Okay? Like in 2003, in 2005, etc. Maybe idiosyncratic volatility was discovered or was at least published after this period, right? But when you look at the performance of some of these big names like Renaissance, right, which is a hedge fund in New York, they were just giving really huge returns. Maybe it was due to that, right? They really found out all these characteristics before somebody published them, and they were just simply training their machine learning models, or their models at least, on these undiscovered or unpublished factors. But in our case, they are assuming that we have this information, okay? And in the same way, when we just come up with this theta is using, let me say, PAMAP range 2015 model, right? But which will be obviously they come up with that factor obviously in 2015, right? I'm not claiming that obviously this graph is realistic, right? I'm just simply saying that if you just train our models and then if you just simply use it on the test data, then this will be the performance.
Thank you, Halis Hocam.
Okay.
With this last question, I would like to end our first seminar of this semester, and I really would like to thank Dr. Halis Sak for his time and for his effort and for such a nice talk. Hope to see you here and hope to have you all again in our next seminar. Have a nice evening.
Okay, thank you. Thank you very much for your invitation.
Thank you, John.
Bye-bye.